class, how are we this morning? Excellent. Recording? Excellent. So, unless my brain is failing me, which it might possibly be the case, I don't think we have any announcements or anything of notes to notes this morning. So we can just proceed automatically with our, right where we left off. Eh? There we go, that's a bit better. So, last time I was explaining the functionality of the call stack, what the call stack is, what it's good for, what it's used for. So, when you guys take Mechatronics 2TA4 or 3TA4, whichever version they have, I don't know if 3TA4 is being destroyed in favor of 2TA4, I'm not sure, but it's possible that that might be happening. At any rate, when you take that class, one of the things that you'll be learning in that class is Microcontroller Architecture. Now, fortunately, Microcontroller Architecture is reasonably similar to general computer architecture, but there will be a number of slides about the function call stack, how things actually work at the assembly programming level, the specific commands that the CPU uses to be able to step in and out of functions. So, it's useful and pertinent at this juncture to have an introduction to these concepts. So, if I recall correctly, last time in class I sort of ended off with a demonstration of how stack frames are generated by function calls using the Python tutor website software thing. Incidentally, if you weren't here last class, Python tutor is an extremely useful website. I'll just, it has a C mode. So, pythontutor.com. What? Tutoring? No. There we go. So, this is just a little tool you can use to visualize your programs. It has a version for C. You'll notice that it's using a current version of GCC, which is the correct compiler. So this is actually a pretty decent way of, check. Like if you wanted to check to see if your program works under GCC and you're under Windows, for example, this might be one way to do it. But when you write a program, you get a nice visualization on the side of where you're not only what variables you have held in memory and how they change as the program computes, but you also have a view of where it's being stored in memory. So, in the case of all local variables get stored in the stack frame, right? So, for example, let's just say we had, I'm going to recreate the factorial thing from last class. Factorial takes integer n. I'm teaching too much Python. If n is less than or equal to 1, return n, or not n, return 1, else return n times n minus 1, or factorial of n minus 1, I should say. There we go. So this is the sort of, oh my God. There we go. It's going to be one of those days. Factorial 5. There we go. So, as we step through the execution of this function, every time factorial is called recursively, it opens a new version of factorial on the stack. This blue highlighted stack frame is the top level of the stack. With respect to the system call stack, the top stack frame is always represents that function which is currently being computed. This kind of breaks down a little bit once we start talking about multiprocessor architectures, but let's just keep it simple for the moment and imagine that we're all using single processor architectures for the moment. Single processor architectures only have one line of execution which they can perform at the same time. All, like, the bottleneck on a single processor for the number of processor instructions you can compute at one time is 1. You can only process one instruction at a time. You just do, several billion of them per second, and it gives the illusion of being able to do things simultaneously, in the same way that running a bunch of still images together gives the illusion of animation. But we can't, we always only process one function at a time, assuming things are nice and simple for the moment. So, when we're trying to execute this iteration of factorial, this one is on pause, and main is also on pause, right? That's another way to think about it. So, I'd just like to throw a few variables in this, just to be able to see what's going on a bit more. So let's just make a dummy variable foo, which will hold the value of n. Replace foo everywhere we had n. And then we have bar is 5. And we're putting bar in there. So that's just, it's exactly the same program. I'm just performing a few intermediate storages of variables so that we have a little more memory to look at, right? So, stepping through this, you'll notice that within these stack frames, right, we have several declared instances of foo holding different values depending on what stack frame you're in, right? You guys, I think I asked you yesterday if you had been exposed to the concept of local versus global variables, right? The naive way of thinking about local versus global variables is to think of them as a two-level system, right? A variable is either local or it's global, right? That's not really how things work in reality. The local frame contains its own variables for the running instance of the function represented by that stack frame, right? Global variables, in this context, would be held all the way up in main, or even, they're held in main, and functions which are not main are given read permissions and write permissions on global variables. That's what defines a variable as global. The idea of accessing a global variable is the same as the idea of accessing data in a stack frame that's further down the stack. Now, this particular set of stack frames stops at main, right? But this is, again, not quite true. Main itself is being called from the shell that ran the executable in the same way that main runs functions from itself. Does that make sense? The stack itself, it goes deep into the operating system with stack frames. This is how, main itself can access system information and system variables, right? So the reason that local variables are only accessible while you are running an instance of the function is because when this function closes out, the memory which has been allocated to that stack frame is deallocated. That memory is released back to the operating system and will be used the next time a function is called to that depth to provide a stack frame for that next calling of whatever the function is going to be, right? So the reason, the actual physical reason in terms of physical hardware memory, that local variables do not exist outside of the functions that call them is because the memory they're stored in is deleted upon completion of the function, right? This is why you can't access foo outside of factorial, right? Because it actually doesn't even exist. There's no reference to it. Does that make sense? Good. Any questions? Good. So, really, you know, especially when you're in a recursive situation, this is a recursive algorithm, by the way. Any function that calls itself is a recursive function. When you're in a recursive situation, it's not really correct to think of there being one version of the local variable of the function. Each time that the function is called, it produces a new set of local variables at the most local level, right? So modifications here won't show up again until execution returns to this stack frame, right? Make sense? Whenever you're in a function, whenever you're accessing a local variable, you are, by default, always accessing the most local version of that variable. Make sense? Cool. I bet they didn't teach you that in 1MD3. No, not 1MD3. Whatever the course code is, 1P13, is that it? Yeah. I bet they didn't teach you that in 1P13. So, good. Now, you guys want a cooking metaphor? Is that useful? Okay. So, let's imagine that we are trying to bake a pie with recipe cards. And the recipe card for the pie references 3 other recipe cards in the same box. We will call them complex ingredients. So, to make our pie, we require flaky pastry dough, we require lemon custard, and we require simple meringue. The method that the computer would use to bake this pie: proceed until a complex ingredient is called for, then take the corresponding recipe card and place it on top of the card which is using that ingredient, follow that recipe. When that complex ingredient is finished, you remove that recipe card, put it back in the box, and continue from the place you left off in the recipe that you interrupted to make the complex ingredient. Right? Make sense? In this metaphor, complex ingredients are, of course, functions. The recipe cards themselves are the definitions of the functions that are stored in RAM, right? So the computer will bring out the instructions corresponding to that function when that function is called for, follow those instructions until that terminates, then put it back, right? In actual technical point of fact, what it does is it manipulates the program pointer to the inside of the function and then back to where it was. So it's like, you know, it's like an arrow jumping around a bunch of recipe cards that are laid out on the table, but, you know, that's how things are organized with the stack. Does that make sense? Cool. So, an example. So let's consider the following function, or the following program. We have a function, square, simply returns x times x, right? We have main defining an integer variable a, and we are simply printing a squared is a, you call the square function on a. Make sense? Very simple, right? 10 squared is 100. So, I think this is kind of already like pretty similar to the example I gave you, but we'll go through it anyway. So, from our operating system, we invoke main. Main gets put on the system call stack. This code, right, corresponds to this stack frame. So we have the automatic variable a. Incidentally, C has several different classes of variable, which we'll talk about. Automatic variables are just variables in the normal sense that the word is used. Variables with no modifiers are automatic variables. They behave and perform precisely as you would expect a normal variable to behave. So we have our stack frame for function main, right? It keeps track of its return location inside of the operating system. At a certain point in execution, we hit the definition of square. Square has its own code. We jump to that code. We then have two things on the stack frame. A definition for square and a definition for main. Notice that this is in the reverse of the direction that appears in Python tutor and the reverse of the direction things exist in actual memory, but it makes more sense with the top of the stack language. So, it's also storing its return location inside of main so that it knows where to go back to. Once the return result has been computed, it is substituted into the expression in which the function call existed. The calculations inside of main then proceed as they were before. It's important to note that you do not need, there we go. It's important to note that you don't need to be between statements for this to happen. You need to be between object code instructions. And since a single expression expands to many object code instructions, basically this is why you can step into a function in the middle of an expression. Make sense? All of the temporary memory that's being used to compute the expression is stored in stack memory and then retrieved when you return to that expression. Okay. Good. So let's talk about variables and how variables are passed into functions. All right? Yes, that's right. We're doing a deep dive on functions. We're going to teach you how actually functions work. So, there are two primary ways that programming languages will pass data into functions. You have languages which use pass by reference, and you have languages that use pass by value. Languages using pass by reference include Perl, Visual Basic, Fortran, and a number of others. Those are just some examples. Variables in pass by reference are passed into functions as references to data rather than the data itself. If I were describing this in about 4 weeks' time, I would say they are passing the pointer to the data, not the data itself. modifying the function argument inside of the function will modify the variable being passed into the function, even as seen from outside of the function call. So basically, what you got, right? If this is the call stack, in a pass by reference situation, if we have a variable x is equal to 7, and we have, function foo, right? If foo has been given x as an argument, then you don't make another x and have it as 7. What you have, it's a little bit, I'm gonna rephrase it a little bit. So let's say foo int y, right? And the invocation line here is foo x, right? So it's got a different name here. That might be less confusing. So our y argument here does not have the value 7. It's not given the value 7. In pass by reference, it's given, sorry about that, it's given a reference to the memory cell in the calling function. So assignment to y inside of a pass by reference situation will modify the data in the calling stack frame. You might be saying to yourself, okay, so that's how things work in call by reference, but I have read it very slightly ahead in the slides and seen that both C and Python are pass by value languages, so why are you even telling me this, right? Because while C does pass by value, it can also pass references by value, which I know is a little bit confusing, but if the input to a function is a pointer rather than a value, this is the situation that you're in, even if you are in a pass by value language like C. In fact, that is how such languages are constructed, using other languages that know how pointers work. Right? Make sense? So with pass by value, right, in a pass by value system, the same operation in the same situation, y would actually be given the direct bit value that's been passed in, thus separating it from the calling function. Modification of y within this stack frame will stay in this stack frame because it's not making reference to the previous. Make sense? A little bit? Any questions? Okay. Modifying an argument does not affect anything outside of the function's local context. C can pass by reference using pointers, but you have to do the legwork yourself. That is to say, you have to pass a pointer and then dereference that pointer to access the data that the pointer is referencing. But again, we haven't talked about pointers yet, so let's just save that for a later date, shall we? So this is kind of a bit random. And now for something completely different. Let's talk about type definitions. So in C, it is possible to create one's own definitions for types. Although you don't get to escape the everything is an integer under the hood paradigm except for floats. Everything is still integers of various size under the hood, but you can create special names for specific sizes and configurations of integers if you want, by using the typedef statement. Typedefs go basically either right after your include statements or right after your function prototypes, wherever you think that's most useful. Probably before the function prototypes, because you might want to use the types you're defining in the function prototypes. So just sneak that in right under the include statements. So the way that typedefs work, you have the typedef keyword, then you have a set of defined type keywords, and then the final one is the name that you are giving them. So you might find it inconvenient as you're programming along in C to have to write out unsigned char every time you want an unsigned char. Unsigned chars are just single bytes, so you might rename it as byte, and you're off to the races. You can just type byte everywhere that you want to use that data type instead of unsigned char, unsigned char, unsigned char. It's like long unsigned float, or long unsigned int, something like that. You know, these type definitions can get quite long with all the modifiers. Not to mention, this is going to come up again once we start defining custom data types with structs later in the course. So after this becomes a valid line of code declaring a variable of the type that's been defined here, right? Now, I will sometimes refer to these as type synonyms. Everybody know what a synonym is? Anybody not? It's two words that mean the same thing. The compiler will swap the type's synonym in at compile time. So this basically sets it up as a preprocessor step. Before compilation, byte will be exchanged for the definition that you've assigned it. So from the compiler's perspective, this thing doesn't even practically really exist, right? But it can be very convenient for human purposes. Smelly human purposes. So, type synonyms can be very useful for improving readability, and as they allow for more descriptive type information. By convention, data types are capitalized. Any questions? Yeah.
So, like, can you only do operations with the same type?
C doesn't really care about types really. Yeah, so the operations, like if you use integer arithmetic on a character, it will work as integer arithmetic on the underlying binary coding of the characters, right? Like, for example, let's just run a very quick experiment. Print d plus d equals d, but rather than give these integers, let's give them character constants. So space plus a. And let's just comment this out. I've been teaching too much Python lately. So first of all, you notice that despite being an apparent type incompatibility, that compiled with not even a warning, right? So yeah, right? Oh wait, no, I'm sorry. I forgot the last. I messed up. I'm sorry, guys. Give me a second here. Oof. Oofta. There we go. I forgot the bit where we actually add them. Right? So I am performing integer arithmetic on things that look like they're characters, but they're not actually characters. Everything is binary in C. Make sense?
Yeah.
So this is, so what was your question again?
Yeah, like any operations between like types that I declare with like integer.
Everything defaults to int.
Okay.
Yeah. Even enumerations, which we're going to see in a little bit. But this is like this is an interesting one, right? So let's say we had, for example, floating point number. Another interesting one is like going between floating points and integers, which is actually a question that a couple of students in my class had the other day. So I think it's sufficiently interesting to bring it up. So let's take some floating point number, view it as both a binary encoded integer and as an actual float. So let's make it 1.2345. Yeah? Oh, I did the thing again. Gotta be, there we go. Sort of, there we go. Oh, I forgot the new line. So this is the line. I forgot the new line character. But you can see the interpretation of a floating point number as an integer works, sort of. You do get an integer out of it. It's like this big, long negative number, right? So, how much did they teach you guys about floating point representation? Not much at all? Have you ever heard the word mantissa? Okay. This is probably a very useful tangent, not in the slides. Let's just follow the journey, shall we? Because this is also very important to understand in general. And I can't believe they didn't teach this to you last year. It's another, I can't believe they didn't teach this to you last year moment. So, y'all have any idea how floating point numbers are actually represented in binary code? Like any concept whatsoever? Okay, so, first of all, we must learn the difference between a float and a double. All right? Floats in C, I'm going to talk about C because this is a C class. Floats are 32 bits. Doubles are double stands for double precision floating point number, right? So it's a 64-bit number. I'm going to talk about doubles, right? So you got 64 bits. Our object is to represent numbers with fractional components, right? So, y'all know scientific notation? In scientific notation, of course, we have, some number x multiplied by 10 to the power of y, right? This is not quite how things work in computers because everything's base 2. Right? So, whereas that's scientific notation, floating point representations are some number x multiplied by 2 to the power of y. Because everything is binary. Right? So, what a floating point representation actually does is it combines a representation of this x with a representation of this y in combination with 1 bit for the sign, right? So we get 1 bit for the sign. It's either positive or it's negative, right? And now you have to decide how to split the rest of the number up between the x and the y component here, or the exponential component and the fractional component, right? So it turns out that this is actually, fortunately being standardized by the IEEE and the IEC. All computers which desire to interact with other computers, which is pretty much all of them, they all follow the same floating point standard. This is the reason you can send a number in Germany and read it in South America and it's still the same number, right? Because everybody's following the standard. The standard is you have 11 bits for the exponential component, right? And then you have the remaining, if this is 64 and this is 1, how much is left, folks? 52. The remaining 52 bits all encode the fraction, right? So, of course, you're not going to get like something that looks like an integer if you just look at the bit values and interpret them as an integer. Because look at all the stuff that's going on here, right? This is a number with a fractional component of 0 and we still get that kind of a number, right? Or not fractional, it's an exponential component of 0, we still get that kind of number. So this is interesting, right? Because you've got some interesting weird effects with floating point numbers as a consequence of this that you absolutely need to be aware of if you're going to program properly. And I know I say that a lot, but this time it's actually true. This particular one is a problem that is like a common pitfall. People get this error and have absolutely no idea where the error is coming from, and they'll re-implement their whole algorithm 6 times and they'll still have the error, and it's very frustrating, and it's because they don't know where it's coming from, right? So the fractional component itself is stored as a series of 1s and 0s, right? So you'd have 1.011010001, etc., right? This works the same way as decimal representations. It's just the base is 2 rather than the base being 10, right? So rather than being, 10 to the 0, 10 to the negative 1, 10 to the negative 2, etc., etc., you have 2 to the 0, 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, etc., right? It's a base 2 system, right? So this number is 1 plus 1/4 plus 1/8 plus 1/32, 64, 128, plus 1, 256, 1 over 256. That's what that number is, right? Make sense? You with me so far? So the only numbers that can be represented with exact precision using this representation are numbers which have a power of 2 as the denominator. So you only have exact representation inside of this system when it's x over 2 to the y, right? Just okay, you guys know how if you put 1/3 into your calculator, you get infinitely repeating 3's? It's the same effect. Under the decimal system, if you try to how do you equate 1/3 as some x over some 10 to the y? Doesn't work, right? Doesn't fit exactly, right? Because, you can be like, oh, well, I'll just multiply by 10 here, but 30 is not, there's no y such that 10 to the power of y is 30, right? There's no way to represent it. Therefore, the consequence of that is under the decimal system, the number 1/3 requires an infinitely repeating series of digits to represent. And because the calculator can only represent 8, 9, or 10 of them, that's how many it represents, and then it throws the rest away. right? So, holding all of that in your brains, the same can be true with numbers in the base 2 system. And the base 2 system, because everything in computers is binary, the base 2 system is what the actual underlying representation of the number is in the computer's memory system, right? So, you get funny effects. Like, for example, 1/10 does not have exact representation in floating point arithmetic, because that's not a power of 2, right? So, what you actually get when you write 0.1 in the computer is not 0.1 itself. You get a very close approximation of it, to like 15 decimal places or so, which, to be fair, very close approximation. But, nevertheless, it is an approximation. So I'm just going to do this in Python because it's quick and, I know I hate Python, but, sometimes it's useful. So let's say we had 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, you take 0.1 and you add it to itself 10 times. What do you get? Under normal math, you get 1. Whoopsie! Not 1. There are certain operations that you can perform which make these very small approximations add up to the point where you can force them out and you can see them. Right? So, so here's a question. If that's true, is that equal to 1? No. So, the moral of the story is that you should never, ever, 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 for any reason, use equality operators on floating point numbers. Ever. For any reason. It's not predictable which situations it will work in and which ones it won't work in. Right? Because it's not predictable whether or not it'll work, you should never use it. Right? So you might ask yourself, but certainly it is reasonable to expect to be able to perform equality comparison on floating point numbers. How would we do it in the absence of the equality operator? This is how you would do it. You subtract the 2, you take the absolute value of them, and you check to see if that's less than some small number. And it can be almost as small as you like. So what the equality operator is actually doing is it's going bit by bit and ensuring that the two numbers are exactly the same, right? In terms of their underlying bit representations. That obviously will not be the case. So I used an integer there just to convince you of the fact somewhat more firmly. I'll make this a float, and you see it still comes out false, right? This has finite representation. These do not. Therefore, equality will fail on them, right? So what you're doing when you're using the subtraction absolute value method is you are checking it within a very, very small range rather than checking for precise precision. Make sense? Cool. Any questions? At the back, sir.
If you multiplied 10 by 0.1, would it also be that, like, the repeated 9s for your loading?
Let's see. Oh, sorry, yeah. There we go. Getting my ones and my zeros mixed up. So it happens with some operators and not others, right? But because it doesn't work for some operators, you should never assume that it works for any. Just conservative engineering principle. Question?
Would this explain why if you do a bunch of like arithmetic on a floating point number, you may end up with a random 0.0005 stuck to the end of your number?
Yes. Yeah. Except 0.00000000. Yeah. Actually, it's kind of interesting. Let me see if I remember how to do this. Format 0.1 in 0.60f. Yeah. So this is what, if you expand all of the decimal places that it's hiding from you, normally they cut it off, like even most reasonable representations will cut it off around here. You can see, again, it's not 0.1, it's a very close approximation of 0.1, right? Now, how you have a number which is slightly more than 0.1 added to itself 10 times, resulting in a number which is slightly less than 0.1 is magic math. I haven't figured it out yet, but you know. This should just underscore the unreliability of floating point numbers for exact mathematics. All right? Question? Well, here's the question. If you're rounding the floating point number, are you still getting a floating point number as the result? Maybe if you've rounded, yes, if you are rounding things to an integer, then everything's fine because this does not happen with integers, right? But if you're rounding to like 1 decimal place and your number would round to 0.1, this is the number you're going to get because it will round it to the closest approximation of 0.1 that it can, right? The rounding function does not magically make the binary nature of memory go away, right? Make sense? This is how it's actually stored in the memory. Question?
So how would you properly convert float to integer?
Well, there's basically 3 methods for rounding floats to integers. Right? You've got the round function, which does normal rounding as you might expect. You've got a ceiling method, and you've got a floor method. But let's, just for the sake of interest, let's do one more comparison here, see what happens when we typecast. We haven't really talked about typecasting yet, but I guess we will now. So if you take some number, like this, and you typecast it as an integer, this typecasting is like the way that C performs type conversions. Let's see what happens here.
What's that? Just trying to do
I forgot what I think.
No.
There we go. So typecasting yields us the integer 1. So if you put this guy in front of the thing you want to convert to an integer, I believe that's conversion with truncation. It'll just throw out a fractional component. Just to prove this isn't rounding anything, let me just put the new lines in. Just to prove that this isn't like a rounding operation, let's pop it up like that. Oh, it still says this one because I didn't change that one, but so you'll note, I hope, If we cast as an integer 1.8345, the result is still 1. The conversion from floating point to integer via this function drops the fractional component rather than rounding it. Make sense?
Why do they have a separate floor function that affects
Any final questions? Okay. Have a good weekend.